The universe is a strange and wondrous place, filled with mysteries that boggle the mind and challenge our understanding. At the smallest scales, the laws of physics as we know them break down, revealing a world that operates on entirely different principles. This is the realm of quantum mechanics, a world of probabilities and uncertainties, where the very fabric of reality seems to be woven from chance. It governs the behavior of atoms and the particles within them, dictating how they interact and form the building blocks of everything we see around us. In the quantum world, particles don't behave like tiny billiard balls following predictable paths. Instead, they exist in a haze of probability, where their exact position and momentum are not fixed until measured. Imagine a single particle occupying multiple places simultaneously, a concept that defies our everyday experiences. This is the essence of quantum superposition, where particles can exist in multiple states at once until observed. Quantum mechanics also reveals that particles can become linked or entangled in such a way that their properties are intertwined. This connection allows them to influence each other instantaneously, regardless of the distance separating them, a phenomenon that seems to transcend the speed of light. This spooky action at a distance, as Einstein called it, is one of the most bizarre and intriguing aspects of quantum mechanics, challenging our notions of locality and causality. The Heisenberg uncertainty principle further deepens the mystery, adding another layer of complexity to our understanding of the quantum world. It states that certain pairs of properties, like a particle's position and momentum, cannot be known with perfect accuracy simultaneously, no matter how advanced our technology becomes. The more precisely we measure one property, the fuzzier the other becomes, illustrating the inherent limitations imposed by the quantum nature of reality. This isn't a limitation of our instruments. It's a fundamental feature of the quantum world. A reminder that at the smallest scales, certainty is an illusion, and the universe is built on a foundation of uncertainty. As we delve deeper into the quantum realm, we uncover more questions than answers, each discovery leading to new mysteries and deeper layers of complexity. Yet, it is this very uncertainty that drives scientific inquiry, pushing the boundaries of what we know and opening up new possibilities for understanding the universe. From quantum computing to potential breakthroughs in communication and encryption, the principles of quantum mechanics hold the promise of revolutionizing technology and transforming our future. In the end, the universe built on uncertainty is a testament to the boundless curiosity and ingenuity of the human spirit, ever striving to unravel the mysteries of existence. Imagine a coin spinning in the air, neither heads nor tails, but existing in a state of both possibilities simultaneously. This simple image can help us begin to grasp a much more complex and fascinating concept in the world of quantum mechanics. In this scenario, the coin is not just heads or tails, but a blend of both, a superposition of states. This is a crude analogy for superposition, a fundamental principle of quantum mechanics. Superposition is a cornerstone of quantum theory, which describes how particles like electrons behave. In the quantum world, particles don't have definite properties until they are measured. Until a measurement is made, these particles exist in a superposition of all possible states. This means that an electron, for example, doesn't have a single fixed position or momentum. Instead, it exists in a cloud of probabilities, where it can be in multiple places or states at once. This is a mind-bending concept that challenges our everyday understanding of reality. Think of a single electron. It can spin up or spin down. In the quantum realm, it does both at the same time. This dual existence is a hallmark of quantum behavior. The electron exists in a superposition of both spin states until a measurement forces it to choose one. This act of measurement collapses the superposition into a single state. This collapse is what we observe as a definite outcome, but until that point, the electron is in a limbo of possibilities. This ability to occupy multiple states simultaneously is what gives quantum computers their immense potential power. Quantum computers leverage this principle of superposition to perform complex calculations at unprecedented speeds. By existing in many states at once, they can explore a vast number of solutions simultaneously. This concept might seem counterintuitive, even impossible. After all, in our everyday macroscopic world, objects have definite properties. A light switch is either on or off. A cat is either alive or dead. These clear-cut states are what we are used to in our daily lives. But the quantum world operates under different rules. Schrödinger's cat, a famous thought experiment, illustrates this perfectly. The cat in the box is both alive and dead until we open the box and observe it. In the quantum realm, particles behave in ways that defy our classical intuitions. Superposition allows quantum systems to explore many possibilities at once. This ability to explore multiple paths simultaneously is harnessed by quantum computers to solve problems that are intractable for classical computers. They can process vast amounts of data and perform complex simulations that would take traditional computers an impractical amount of time. As we continue to develop and understand quantum technology, the potential applications are staggering. From cryptography to drug discovery, the power of quantum superposition could revolutionize many fields, making the impossible possible. Imagine two coins flipped simultaneously, one landing on heads, the other on tails. Each coin flip is an independent event, and the outcome of one does not affect the outcome of the other. This is a simple example of correlated events, where two actions occur at the same time, but are not causally linked. This is a correlated event, but the outcome of one coin flip doesn't influence the other. The results are purely coincidental, governed by the laws of probability and chance. In classical physics, this is how we understand most interactions. Each event is separate and distinct. Now imagine two particles linked in such a way that the state of one instantly determines the state of the other, no matter how far apart they are. This is quantum entanglement. Unlike the coin flips, these particles are not just correlated. They are deeply connected in a way that defies classical understanding. Entangled particles share a destiny. When you measure the state of one particle, you immediately know the state of its partner. This connection is so strong that it persists regardless of the distance separating them, whether they are a few millimeters apart or on opposite sides of the universe. Measuring the state of one particle instantly determines the state of its entangled partner, even if they are light years apart. This instantaneous connection seems to suggest a form of communication that transcends the speed of light, challenging our conventional understanding of space and time. This connection is not bound by distance or time. It's as if the two particles are communicating faster than the speed of light. However, this communication is not about transferring information in the traditional sense. It's a fundamental aspect of their shared quantum state. Einstein famously called entanglement spooky action at a distance because it challenged his theory of special relativity, which stated that nothing could travel faster than light. He was deeply troubled by the implications of entanglement, as it seemed to violate the very principles that underpinned his work. However, entanglement doesn't violate this principle because it doesn't involve the transmission of information. Instead, it reveals a deeper layer of reality where particles are interconnected in ways that classical physics cannot explain. This mysterious connection is a cornerstone of quantum mechanics. Entanglement is one of the most profound and mysterious phenomena in quantum mechanics. It challenges our understanding of the universe and forces us to rethink the nature of reality itself. Scientists continue to study entanglement to unlock its secrets and harness its potential. It plays a crucial role in quantum computing, enabling the creation of powerful algorithms that exploit the interconnectedness of quantum systems. These algorithms have the potential to solve complex problems that are currently beyond the reach of classical computers, opening up new frontiers in science and technology. Section 4. The quantum computer. A new kind of computing. For decades, computers have relied on bits, the binary digits 0 and 1, to process information. Quantum computers, however, harness the bizarre laws of quantum mechanics to unlock unprecedented computational power. They utilize qubits, which can exist in a superposition of 0 and 1, allowing them to perform calculations that are impossible for classical computers. Imagine a classical computer as a solo musician, playing one note at a time. A quantum computer is like a symphony orchestra, capable of playing a multitude of notes simultaneously. This ability to explore multiple possibilities at once is what gives quantum computers their edge. While still in their early stages of development, quantum computers hold the potential to revolutionize fields like medicine, materials science, and artificial intelligence. They could accelerate drug discovery, enable the design of novel materials, and unlock new frontiers in machine learning. However, building and controlling quantum computers is a monumental task. Qubits are incredibly delicate and prone to errors. Overcoming these challenges is crucial for realizing the full potential of quantum computation. Section 5. Qubits. The building blocks of quantum computation. In the digital realm of classical computers, information is stored in bits, represented as zeros and ones. Quantum computers, however, employ qubits, which are far more versatile. A qubit can exist not just as a 0 or a 1, but also as a superposition of both simultaneously. Imagine a spinning coin, neither heads nor tails, but a blur of both possibilities. This is analogous to a qubit in superposition. This ability to occupy both states simultaneously allows quantum computers to explore many possibilities at once. Qubits can be created using various quantum systems, such as trapped ions, superconducting circuits, or photons. Each type of qubit has its own advantages and challenges in terms of stability, controllability, and scalability. The power of quantum computing lies in the exponential growth of computational space as the number of qubits increases. With just a few dozen qubits, a quantum computer can already outperform classical computers for certain tasks. As researchers push the boundaries of qubit technology, the potential applications of quantum computing continue to expand.